So here's another example, and the good news, it's already in the frequency domain. So we just have to solve it for the Thevenin and Norton equivalent terminals across terminals A and B. Remember, the Thevenin equivalent is just the open circuit voltage between terminals A and B. Okay, but you know there's no current over here because it's an open circuit. So to solve for V Thevenin, thinking about what Drew just asked me, I need to model that mutual inductance. So what I would do is I'm going to redraw this, and I'm now going to put the inductors in series with those dependent sources. Okay. Everybody good? So it's the same circuit, but I now put in the dependent sources to model the mutual inductance. Where I'm going to label this current clockwise I1. It's going to exit at the dot. And this is an open circuit, so there is no current over here, or you can show that it's 0 amps. So the voltage source over here is 60 with an angle of 30 degrees. This resistor is 20 ohms, and the inductor is J10 ohms. This inductor is J20 ohms. Now, because there is no current flowing on this side, even though I have this J5 mutual inductance, this voltage source would be J5 times 0. So it's just 0. This voltage source would be J5 times 0 because there's no current flowing through that right inductor. So that first voltage source is J5 times 0. Over here, I have I1 that enters at the dot. So that means this dependent source over here is positive on the left and negative on the right. Positive on the left and negative on the right. And the voltage source is J omega M I, or J5 I1. Okay. So I'm going to do KVL at I1. KVL at I1 would be 20 I1 plus J10 I1 equals 60 angle 30 degrees. KVL at I1 is 20 I1 plus J10 I1 equals 60 angle 30 degrees. So I1 equals 60 angle 30 degrees over 20 plus J10. What is I1? Put it in your calculator, please. 60 angle 30 degrees over 20 plus J10. What is I1? Sage? 2.68 with an angle of 3.43. Very good. Amps. Okay. So then V Thevenin is the voltage across terminals A and B. So that should be the same as the voltage across J10 I1 and minus J5 I1. J10 I1 minus J5 I1. So V Thevenin is J5 times I1. V Thevenin is J5 times I1.
J10?
Yeah, this is J10. I'll make it look a little nicer, Alfred. This is J10. What is V Thevenin? Winnie? Very good. 13.4 with an angle of 93.43 degrees. Okay. Any questions before we go find I Norton? That's the first value we need. Any questions before we go find I Norton? Okay. So to find I Norton, I draw the circuit again, but now I need to put a wire between terminals A and B. And that short circuit current, or IAB, is I Norton. I put a wire between terminals A and B, and that short circuit current is I Norton. Okay, now I'm closing it up, so I am going to have voltage on both, so I need to put my dependent source back in here. The voltage source is still 60 angle 30 degrees. This resistor is 20 ohms. This resistor is J20 ohms. I'm sorry, the inductor is J20 ohms. This inductor is J10 ohms. The mutual inductance is still J5 ohms. This clockwise current here is I Norton. And this clockwise current here is I1. Common mistake students want to make is, I want to just use the I1 I already made. Not the same I1. If I change the circuit, I cannot use this other I1. I gotta find I1 again once I change the circuit. So I have a clockwise current I1 on the left, a clockwise current IN on the right. I1, the current exits at the dot. That means for the induced voltage, that means that it is negative at the dot. So for that one, it's positive on the left, negative on the right. Positive on the left, negative on the right. Positive on the left, negative on the right. For I Norton, the current also exits at the dot. That means that it's positive on top and negative on the bottom for the first induced voltage. Positive on the top, negative on the bottom for the first induced voltage. So the induced voltage for this left one is J5 I Norton. J5 I Norton. The voltage source on the left is J5 I Norton. The voltage source on the right actually has two things flowing through the current, I1 and I Norton. So for this one, the induced voltage is actually J5 times I1 minus I Norton. J5 times I1 minus I Norton, because the current flowing through this inductor is I1 minus IN. I1 is right here. I Norton is right here. That inductor is shared between two meshes, so the current through it is the combination of the two mesh currents. Good, Noah? Other questions? All right, so just like we did before, we're going to write a KVL equation at I1 and a KVL equation at I2. KVL at I1 is 20 I1 plus J10 times I1 minus I Norton plus J5 I Norton, and that equals 60 angle 30 degrees. 20 I1 plus J10 times I1 minus I Norton plus J5 I Norton equals 60 angle 30 degrees. Are there any questions? Yes, Alfred.
Why does the resistor to the right, why is that modified by I1 minus IN when the other one?
Right here?
Yes.
Because this inductor is shared between meshes I1 and IN, the current through that inductor is what induces this voltage.
Okay.
So that current is I1 minus IN. There's only one current through this inductor.
So that dependent source is reliant on the other inductor.
Correct. That is exactly right.
All right.
So for the other one, we're going to have J20 times I Norton plus J5 times I1 minus I Norton minus J5 I Norton plus J10 I Norton minus I1. And that equals 0. Okay, I'll give you the answer for this one so we can move on. So when you put this in your calculator, you get that I Norton is equal to 687 with an angle of 6.37 degrees, and the units are milliamps. You don't care about I1, you really only care about I Norton. So I Norton is 687 with an angle of 6.37 degrees, and the units are milliamps. So I need Z Thevenin to find the Thevenin and Norton equivalent. Z Thevenin is V Thevenin over I Norton. Find that in rectangular form, please. Find Z Thevenin in rectangular form. And then the last thing we do is draw the circuits. Find Z Thevenin in rectangular form. That's V Thevenin over I Norton. And then we draw the Thevenin equivalent circuit. And the Norton equivalent circuit. In rectangular form, what is Z Thevenin? We normally write impedances in rectangular form so that if it's a resistor and inductor in series, you can see that. So what is it?
0.00101 plus 0.0195J.
You're right, but you're off by a multiple of 1,000, which means that you did not consider that milliamps.
Oh, okay. I see that.
Okay, so this is 1 ohm and J 19.5 ohms. And this is 1 ohm plus J 19.5 ohms. That means we have a resistor in series with an inductor. How did I know it was an inductor and not a capacitor? It's not negative. Very good. Okay. Are there any questions?